Hi one and all, and welcome to today's video on transformations of power functions with positive integer index. Wow. Now obviously if you are here and understand that title, much respect. If you don't understand the title, well hopefully by the end of this video you will. I am Darren, otherwise known as MaffsGuru, and I am here to make maths much simpler for you with my rather unique style. So by the end of this we're going to need to know what positive integers are, what their graphs look like, or what else, how to transform them, and know all those key points that are important to us. And sketching graphs in the methods course is really important. If you are new to my channel, thank you so much for watching and welcome. Hopefully you'll enjoy what I'm about to show you. I try and make maths as simple as I possibly can. If you enjoy it, can you let your friends know that I'm out here? And more importantly, if you can you subscribe? There is a red arrow over there letting you point to very much what it is if in fact you're watching this on YouTube. If not, go to YouTube/MaffsGuru, M-A-F-F-S-Guru. So literally what we've been dealing with in previous videos, and if you haven't been watching the previous videos, where have you been? We have very much been looking at transformations, dilations, reflections, and translations of all sorts of different functions. We've looked at how to build them up from basic hyperbolas and truncuses and square root graphs and parabolas and cubics to more complicated functions. We've looked at how to actually look at two functions and go, we know how to go from that function to that function by using the algebra, and there's been quite a lot of learning. Now the reason we labour this for methods, and in fact lots and lots of mathematics, is because it is so important. Those of you here in Australia and in Victoria, a lot of this will appear in your SAC, okay, or it could be examined in your SAC, but not the easy stuff. We want you to understand. So before we go any further, let's look at the language here. What is an index? Well, an index is basically nothing more than a power or a floating number. So a squared, a cubed, a power of 4. That is an index. And an integer. Surprises me the number of people who don't know what an integer is. And ladies and gentlemen, it is nothing more than a whole number. Okay, so we're looking for whole number powers basically. You know, this fractions and this halves. If we look at the general form for graphs with positive odd integer indices, so what we're basically saying is things like x to the power of 3, x to the power of 5, x to the power of 7. I loaded up my trusty desmos.com/calculator, no sponsorship, and I put in x to the power of 3 and x to the power of 5. And what I noticed, and I've got a very small shot here, is that actually there's a lot of similarities between the two graphs. In fact, they look very similar. The major difference between the graph of, in red here, x to the power of 3 and x to the power of 5 is that x to the power of 5 seems to have been sucked closer to the x-axis. Sounds wrong, I know, really sorry, but it seems to level out more towards the x-axis. And what you would find is if you did x to the power of 7, again, it would be closer still, or it would appear closer than x to the power of 5. But the shape of x to the power of 3 and x to the power of 5 are pretty similar. What are they? Well, they are odd functions because they can be rotated through 180 degrees and they look exactly the same. And the graphs of x to the power of 3 and x to the power of 5 share some common coordinates. Easy for you to say. Put my teeth back in. And they are -1, -1, 1, 1, and 0, 0. Now, the reason we need to know those coordinates is because when we start moving these graphs around, it is vital to be able to show the examiner that you understand. Now, to be perfectly honest with you, no word of a lie, I have seen students who have been asked to draw these things and asked to show some sort of translation and literally have just done this randomly and gone, ta-da, there you go, can I have 14 marks? Now, you're going to turn around and say, well, what's wrong with that? Well, the problem is I have absolutely no reference here to know the translation, the dilations, or the reflections. Now, by putting a coordinate point here, 1, 1, for example, and putting another coordinate here, 3, 4, I can show the examiner that that point 1, 1 has moved over to 3, 4. Hopefully, he says, there is actual evidence when you do the question that that's where it should end up. Obviously, if you've just made that point up and just drawn some random graphs, you're probably going to get no marks. Now, one other thing that's very important to notice here is, do you remember way back in methods 1 and 2 when we did differentiation? And we probably said that when there is a maximum of a curve or a minimum of a curve, there is a 0 gradient. Well, actually, as it turns out, For a cubic, there is also a 0 gradient at that point there. Just the point that it starts to kink or flats out a little bit, and actually at that one point, there is a 0 gradient. That's going to come in really, really important later on because maths is going to try and trick you. So knowing the general shape of that graph, can we now use it to sort of build up again a graph of some sort of transformation? Well, of course we can. All of this needs you to know various graphs. You need to know what a hyperbola looks like, a truncus, a square root graph, a cubic, a x to the power of a third. What other graphs do you need to know? Possibly a circle. There are a number of them, but I will let you know what they are as we go through the course. So we have here a function, and so what we need to do now is work out, well, what is it asking us to do? Well, you look at your dilations, your reflections, and your translations, and notice I write DRT every single time. It's visual, it helps me know what I'm doing. So, dilations, are there any? No. Are there any reflections? No. This is a fairly simple question. Why am I boring myself with this? Are there any translations? Yes, there are in fact 2 that way and 1 that way. So what am I going to do now? Well, the first thing I always do, ladies and gentlemen, is I draw my base sketch. And I say, well, that's 1, 1. And I know that point there is -1, -1. And I know that point there is 0, 0. So that's my base graph. Lots of you guys out there at this moment in time, and by that I mean boys, sorry, stereotypical, will already be going, hold on a minute, I've got to do different graphs. Can I not do all this in my head? If you want to, but if you're wrong, you actually lose all of your marks. If you do sort of individual graphs or you build it up, the chances are in the exam, if you get your final graph wrong, you can actually be awarded marks for your working out, as long as it's clear. So the first thing I'm going to do is just translation of 2 units to the right. So again, I'm now going to draw my axes, and I'm going to draw my graph that's actually going to do something like that. Now obviously I've got to make sure it looks roughly the same, but what I notice is that all of my points are going to have an x value that's going to increase by 2. So this point here is going to be the easiest to do, which is 2, 0. This point here is going to become 3, 1. And this point over here, for example, now let's work out what that's going to be. It's going to be 1, -1. So this point here is 1, -1. Now it doesn't look particularly accurate. Maybe I should have worked out my coordinate values first and then drawn the rough graph. There's something else I'm going to have to do in a moment, but I won't rush it. So now we're going to move the whole thing up by 1. So let's see what happens now when I actually do my coordinates. So when I move it up by 1, all of my y values are going to increase by 1. So I'm going to have 1, 2, 3, 2. Let's say that's 3, 2 now. And then we've got 2, 0 that becomes 2, 1. And then 1, -1 is going to become 1, 0. So again, we have to put that in, yes, 1, 0. We have to write those in coordinate form. And so now we've got this with a bottoming out and that. All right, so there we go, ladies and gentlemen. Is that my final graph? Well, sadly not, because actually if I go a little bit further down, there is going to be an intercept here and an intercept there. So zooming in just a little bit. Whenever you draw these graphs, and yours are always going to be big enough to fit on a decent size axis, wherever the graph crosses the x or the y axis, you have to write those coordinates. You also have to label your axes, x and y. You need to make sure that there are arrows on the end of those lines if the domain is not limited. All of these things all happen and all will be taught as we go through the course. Most of it you will already know. But how on earth do I find my x and y axis intercepts? Well, ladies and gentlemen, it's not actually that hard. He says, so scrolling back in and going back to my original function, we had y was equal to x minus 2 all cubed plus 1. So I suppose the first thing we're going to do is find the y-axis intercept. How do we do that? Well, we let x equal 0. And it's literally that easy. The easiest one in the world is to find the y-axis intercept. So we have 0 minus 2 is minus 2 all cubed plus 1. Minus 2 all cubed is actually minus 8, plus 1 gives me minus 7, and so I now know that is 0, minus 7. Please do not just write minus 7 on the axes, it is 0, minus 7. That was probably the easy one to do. How about the next one? Well, we make it equal to 0. So this time, y is equal to 0 because we're trying to find the x-axis intercept. So 0 is equal to x minus 2 all cubed plus 1. So x minus 2 all cubed is equal to minus 1. We're going to take the cube root of both sides, which gives me the cube root of minus 1, which just so happens to be minus 1. Yes. And we're going to add both 2 to both sides, which gives me 1. So, ladies and gentlemen, and you're going to say, you didn't need to do that, MaffsGuru. And I know I didn't, because actually I'd already got my intercept here. But it didn't hurt to check. Because at the end of the day, you want to gain as many marks as you can. And for that extra 15 seconds it took there to check it would make life so much easier. And again, I've put in a red box here, and it comes again a bit later on. You must do x-axis intercepts, y-axis intercepts, turning points, yes? So we knew that for my cubic, there was that turning point in the middle, otherwise known as a stationary point or a point with 0 gradient. Endpoints, when the domain is limited, equations of any asymptotes, and at least one coordinate point. So actually, for the graph I just drew, tick. The examiners would be pretty happy with that. What about this one here? So we have, again, dilations, reflections, and translations. So are there any dilations? No. Is there any reflection? Yes, there is. There's this reflection here. So the graph seemingly is reflected in the x-axis. There's a reflection in the x-axis. And then there is obviously a translation of -1. So 1 unit that way and 2 units up. Seems very, very similar to my last one. Let's see what happens when we build this up bit by bit by bit. Okay, so let's draw my base graph first. A quick sketch just to see what it looks like. Yep, we've got that point there is 0, 0 again. We have this point here is -1, -1. And that point there is 1, 1, because we're dealing with that cubic. So dilations, none. Reflection in the x-axis, so it's going to reflect that way. So now that means that -1 becomes 1, 1. So that becomes, that's rubbish, try that again, -1, 1. My y values become positive. That one there stays as 0, 0. And 1, 1 becomes 1, -1. Yep, so there we go. So we got 1, -1. And so trying to draw this graph properly, we're ending up with this. All right, and again, it's just a sketch. You'll be able to draw it much, much easier. So there's my reflection. Thank you very much. Now I'm going to translate it, same deal as I had before, so we'll break it down bit by bit by bit. First thing, I'm going to move it right, trying to do it for the camera, one place, okie dokie. So I've got -1, 1, I'm going to move it right, so that's going to give me -1, that's going to give me 0, 1, can I add 1 to each of the x values? This one here is going to give me 1, 0, and this one over here is going to give me 2, -1. Awesome! So again, we come down, we're going to do this, and my graph is looking not quite as accurate as it should be, but I'm happy. It's got the right form, and now I'm going to move the whole thing up by 2. So again, let's do my coordinates. My y values are going to increase by 2. So that's 0, 3. 1, 0 is now going to become 1, 2. And then finally 2, -1 is going to become 2, 1. So that's sort of there. And again, yuck to the idea of how accurate my graph is going to be. But yay, ladies and gentlemen, we're done and we're finished. Yes? Nope, because we have to make sure that we've got a y there, we've got an x there. We've got to make sure that we put the arrows on the end. And is there anything else I need to do? Yes, I need to make sure I've got my x and y axis intercepts. Now the good news is, I've already got my y-axis intercept. How do I find my x-axis intercept? This is too complicated. Well, no, it isn't. Not really, because what I'm just going to do is use my equation y is equal to -x minus 1 all cubed plus 2. And to find my x-axis intercept, I'm going to make my y value equal to, yep, 0. So 0 is equal to -x minus 1 all cubed plus squared. Take away 2 from both sides gives me -x minus 1 all cubed is equal to -2. The minuses cancel each other out. So I'm going to take the cube root of 2. So x minus 1 is equal to cube root of 2. Now, not plus or minus, that's only square roots to the power of 4. So it's just that one solution. And so x becomes equal to 1 plus the cube root of 2. And there we go. And you're going to say, how do I put that on my graph? Do I have to work that out? Do I do it as a decimal? Well, over here for the methods course, no, it is not written as a decimal unless the question tells you otherwise. So what you would be doing there is you would literally write 1 plus the cube root of 2, comma, 0. And you would leave it in exactly that format. Ladies and gentlemen, I am fairly happy with that graph there. Have I complied, or have I made sure that I've done x-axis and y-axis intercepts? Yes, thank you. Turning points, there weren't any. Endpoints, done because I've got my arrows. Equations of any asymptotes, there aren't any. And have I got at least one coordinate value? I do. Well, ladies and gentlemen, that would be it, wouldn't it? Sadly not. Barry's been at us again. Who's Barry? He's that dude who makes life actually quite complicated. Sorry about those of you who've got motion sickness now with what's happening behind me getting bigger and smaller. Size isn't everything. Now obviously Barry wants to turn maths on its head, and how does he do that? Well, he does that by throwing curveballs. And in many cases, they'll give you questions here where actually they say, here is the general form of an equation. Here is the general form of a cubic. And all we're going to do is give you some information to help you find the equation. Now, reading this information is the key. And they're going to throw curveballs and they'll throw tricks. And one of those tricks for this particular question is a zero gradient. But let's not rush ahead here. So this question has been extracted from the Cambridge Mathematical Methods, Units 3 and 4 textbook. Cambridge have very kindly given me permission to use their examples in these videos, and I am stoked because you get taught the stuff you need to know. None of these made up examples by other tutorial series. So we now know we've got a graph that is y is equal to a, x minus h all cubed, plus k. Now, to be able to use this, you've got to realize where these particular values come from. So if you remember, this a is actually a dilation away from the x-axis. But what about this h and this k? Well, that's the translation vertically and horizontally. But how on earth do I use the information? What does this zero gradient at 1, 1 mean? Well, the first thing we need to realize is this is a cubic. And if you remember from the cubic, that point of zero gradient was actually originally at 0, 0. It's now telling you it's actually moved to the point 1, 1. So really bad sketch, but 1, 1. So what they're trying to tell you in a sort of tricky way is actually we've moved 1 unit to the right and 1 unit up. And so before I even know it, I know the value of h and I know the value of k. Well, k is 1. Because we've moved 1 unit up, and we just need to check that if we move to the right, then actually that's in the positive direction of the x-axis, and so h becomes 1 again. That one piece of information, everyone would look at that coordinate and go, oh, what do I do with that? That wasn't the important thing initially. It was knowing that zero gradient. So knowing that, I can now say that y is equal to a, x minus 1 all cubed plus 1. Well, how many unknowns do I have now? 3. I'm trying to find the value of a, which means to know I need an x and a y value, and just so happens they've given me an additional coordinate. And we now know that a coordinate is nothing more than an x and a y value in code. So I now know that x is equal to 0 and y is equal to 4. So I get 4 is equal to a, x minus 0. Oh no, what am I doing? I know that x is 0, so 0 minus 1 all cubed plus 1. So I'm going to take away 1 from both sides to give me 3. I know that 0 minus 1 is minus 1, and minus 1 cubed is in fact minus 1. So I get minus a is equal to 3, and so a is equal to minus 3. And that's where I leave my answer. I move on, and thank you very much, don't I? No. Because the question said find the values of a, h, and k. And so in this situation you say a is equal to minus 3, h is equal to 1, and k is equal to 1. And my advice to you is just hedge your bets and say, therefore, y is equal to minus 3, x minus 1 cubed, plus 1. Not going to hurt to put that down as well. All right, so that was that. And then back to the stuff we know. Again, see how we keep changing directions. Again, extracted from the Cambridge Mathematical Methods, Units 3 and 4 textbook. Find the rule for the image of the graph y equals x to the power of 5, y equals x to the power of 5 under the following sequences of transformations. And there are 2 ways of being able to do it. There is using the shortcuts, which have come up in my previous video. So let's try that. Reflection in the y-axis. Reflection in the y-axis means my x values are becoming negative. And so I replace x with minus x to the power of 5. Thank you very much. We can do that. Now, I can then multiply that out, which gives me y is equal to minus x to the power of 5. And if you don't know why, oh, you need to do this. You need to do your powers. So there's a tick. Dilation of factor 2 from the y-axis. So it's my x values that are changing. And we remember that when it's the x values that is changing, we replace x with x on a. And a is the scale factor. So I'm going to replace x is going to be replaced with x on 2. So we get y is equal to minus x on 2 all to the power of 5. Yes, and a translation of 2 units in the positive direction of the x-axis. So we're going 2 units that way. How do we do this? Well, replace x with x minus 2. So in this situation, x is going to become x minus 2. So y is equal to minus x minus 2 all on 2 to the power of 5, and 3 units in the positive direction of the y-axis, and so that means we replace y with y minus 3. So y minus 3 is minus x minus 2 all over 2 to the power of 5, and I can't draw a 5 anymore, and so y becomes equal to minus x minus 2 on 2 all to the power of 5 plus 3. Now that's one way of doing it, and then my favorite way is using algebra. So what are we trying to do? We've got y is equal to x to the power of 5. I've got my original coordinates x to the y, and so what I now need to do is try and build up this algebra. So first things first, reflection in the y-axis. So when you reflect in the y-axis, the x values become negative, so that becomes minus x. Dilation of factor 2 from the y-axis. So again, if I'm 2 from the y-axis, that means I double the value of x. So that now becomes minus 2x. Translation of 2 units in the positive direction of the x-axis. So add 2 and y plus 3. Now again, in the situation where you're using the algebra, it works in the way that the language tells you. None of this backwards, do I do it backwards stuff? Nope, it's as it is. And we know that that is x dashed and y dashed. So therefore, we know that x dashed is equal to minus 2x plus 2. And we know that y dashed is equal to y plus 3. Why are we doing this? We're trying to now put that information into my equation y equals x to the power of 5. So we need to rearrange these two equations so I can get y equals and x equals. So we know that y is equal to y dashed minus 3. And we know that if we have 2x is equal to minus x plus 2, so I'm swapping those over, and then x becomes equal to minus x plus 2 all on 2. What does that have to do with the price of fish? Well, now we go y is equal to x to the power of 5. That's the equation we start with, and we're going to substitute it in. So we get y dashed minus 3 is equal to, so where I see an x, I get minus x plus 2 all on 2 to the power of 5. Add 3 to both sides, and we get y dashed is equal to minus, well, actually that should have been an x dash, ladies and gentlemen. Very, very bad. So that should be an x dash, that should be an x dash, and that should be an x dashed, plus 2 all on 2 to the power of 5, and then plus 3. And you're going to say, hold on a moment, they do not look the same. But actually they are, because I can move this minus side outside my brackets. Just to finish this off for completeness, I don't need the dashes anymore, that y is equal to. So what I'm now going to do is square brackets. I'm going to move minus 1 outside of the top there, which gives me x dashed minus 2 all over 2 to the power of 5 plus 3. And so, ladies and gentlemen, we know that minus 1 times minus 1 times minus 1 times minus 1 times minus 1 is in fact minus 1. So that becomes minus 1, or in fact just minus, and my brackets become x minus 2 on 2, all to the power of 5 plus 3, and lo and behold, there they are. They are exactly the same. Now, which one of those you use is totally up to you. It's personal preference. I have to say, I really like the algebra. It makes a lot more sense to me, and hopefully I'm not going to make any mistakes. But we've come pretty much to the end of another video. Hopefully you're realizing that, to be perfectly honest with you, there's nothing different that I'm teaching. I'm just changing different functions. We're just practicing over and over again how to use the algebraic techniques we've got, or the graphing, or whatever else. please, if you are following this course or any course that's dealing with transformations, just practice, practice, and practice again. All right, I am pretty much done. Thank you so much for watching. It is, as ever, really good to see you. There is a circle loading over there that if you haven't already done so, can you subscribe? Can you tell your friends? And can you absolutely come back? There's a video loading slightly below it, also part of this series. It's been good seeing you. Thank you very much. MaffsGuru out. I'll see you next time. Bye-bye.